All right, class, welcome to Math Stats. This is the material for Friday, April 3rd. We're just going on to the next section. In some ways, it's similar to what we've been doing, but because of the nature of it, we'll do things quite a bit differently. And the good news is the idea that we present here, a way to test our hypothesis, we'll be able to use for other tests. Excuse me. So, section 6. Remember section 5, we were testing hypotheses about the value of theta, a proportion from a binomial population. And just like before, we went from mu to 2 mu's and then from sigma to 2 sigmas. We want to extend it from one binomial population, and we're going to jump all the way to k of them. We could work out a detail if there were only 2, like we did earlier in the chapter for other parameters. There's a homework exercise that has you do this, and we'll see if I assign it. If I do, then you'll get to fight through it. I probably won't assign it because we're going to run into the same problem in a little bit different context, and I think I'll assign it there. So, section 6, we have k binomial populations. Now, you can run this test no matter what those populations are, but it's not going to mean anything unless they have some similarities. In fact, they should be similar in as much as possible with respect to one variable. So for example, maybe a city wants to know the percentage of residents above 50 that are on welfare. And maybe they would like to know how that compares to several cities across a given state or region. So we have binomial populations, the percentage of people in that population that are on welfare. And we can think about k different populations, k different cities. So we wouldn't really want to compare, the percentage of people on welfare to the percentage of high school students that graduate on time. We could do it. We know how to do it, but it's like totally meaningless. So we have very similar populations, differing only in one aspect. And then we want to know, in a city, you might want to know, like, are we ahead of the curve or are we behind? How do we respond to that? So we're going to test the hypothesis that theta is the same for all of these populations. I'm going to work through the details for that test that you see on the board right there. All thetas are the same. We can modify it with just a few little tweaks. Maybe someone says, 40% of the people are on welfare. Then we can actually include the possibility of testing it against some established constant. And most of the details are the same. What I'm going to do is, in my experience, that seems sort of rare. It seems like too much to ask for, that they are all the same and that they all are some pre-specified value. So I'm going to work it for this hypothesis, and then at the end I'll tell you 2 little differences that we'll do if someone claims a predetermined value for all of those thetas. And now, we've been having, I think on all of the tests we've done, we've had 3 possible alternate hypotheses depending upon the research thesis. But now there's only one. That is, if those thetas are not all the same, then at least 2 of them are different. So there you have it. Theta I is unequal to theta j for some I and j. So we go out and do a random sample in each of our populations. I didn't write it on the board. It's in the formula up here. The x's are the number of success. I can add it right here. So this phrase no goes right up there. So the results of our samples gets us the number of successes in each population. We'll call those x's just like we've been doing, x1 to k. You can see that. Cool. All right, so we'll take those, and then we can, for large n, and each population has its own sample size, n sub I equals 1 to k. We can, for large n, we can normalize that. So up above is the way we've thought about that. Xi minus ni theta I is approximately z, a standard normal. Now, if the null hypothesis is true, all those thetas are the same. So we don't really need to put theta I in there. We can just put theta. And because we don't have a hypothesized value, theta 0, we're just going to use the estimator that we know is the best. If all of these populations have the same theta, then all of the information from my sample informs me. It gives me information about theta. So we're just going to put them all together. The total number of successes divided by the total sample size. That's our estimate. If the null hypothesis is true, everything gives me information about that common theta value. Total number of successes divided by the total sample size. All of the ni's added together. All right. So we're going to replace theta I with that. If the null hypothesis is true, theta hat is our good estimator for all the thetas, so it's going to slide into those slots. This is true for every population. This form, given large sample sizes, approximately standard normal. Now, when we had a test about two means, we were able to use the distribution of x1 bar minus x2 bar. We knew what it was under general circumstances. We worked out those details in chapter 8. When we had two sigmas, we knew that we could form the ratio and we would get an F distribution. If we were only looking at two thetas, two binomial populations, we know the distribution of theta 1 hat minus theta 2 hat, and we could devise a test. For some reason, this is what I talked about earlier, we could do that and kind of mimic what we did for means back in earlier in the chapter. But the author doesn't devote any extra time to the case of two thetas. He jumps right to K. Actually, I should say they, he and her jump right to K. And now how are we going to do this? We can't like do a single numerical calculation, subtraction or division like we did earlier for respectively the mean and the variance. So we need a whole new approach in order to handle, as soon as we get more than two, there's no simple way to arithmetically talk about the distribution of the data that we get. So we're going to go a different direction, and this is the direction that we're going to use in later tests. Instead of focusing on the standard normal that each one is, we're going to square it. And we know that when you square a standard normal, you get a variable that's chi-squared with 1 degree of freedom. Okay, and we also know it's easy to believe that our samples per population are independent. I mean, they're all individually in the populations. So if I add up a bunch of independent chi-squares, I get a chi-square. Now, there's one technicality here, and unfortunately, this is complicated. Okay, the authors refer you to references at the end of the chapter. If you want to dig into why this is true, you can go look for that. But basically the concept, and we don't have proof of this, we're just going to believe it, is when I replace a parameter with an estimate in the background of a chi-square or F distribution, then using a estimate instead of a parameter, it adds more variability. And the way we're going to compensate by that is reduce the degrees of freedom by 1 for every parameter that we're estimating. Okay, here we're only estimating 1, and that is the common value of theta. We're doing all our calculations as if the null hypothesis is true. So we're just taking, that means all the thetas, in fact, I could, like under the null hypothesis, I could get rid of those sub i's because we're assuming they're all the same under the null hypothesis. We're replacing that theta parameter with an estimate. Our degrees of freedom go down by 1. There's more variability. So we certainly can agree the degrees of freedom need to go down. That increases the variability. Why down by 1? Well, that's just what we're going to do. So that's what the star is for here. Instead of having k degrees of freedom, we're going to have k minus 1. And again, if you're curious, and if you dig into this and you get some ideas, it would be fun to talk about it. You may have a chance to teach me why that's the way we do it. But anyway, this is our statistic right there. You can see that. And we need to compare that to a critical chi-square value because we believe that has a chi-square distribution. So how do we do this? Well, let's think for a minute. If the null hypothesis is not true, or let me say it this way, if the null hypothesis is true, we would expect all of our theta values per population to be pretty close to the common value. If it's not true, and therefore we would expect the z-score to be pretty close to 0. Okay, when this can be, of course, positive or negative, but this guy can only be positive. So if the null hypothesis is true, most of these values are close to 0. If they're negative, we'll square them, but they ought to be pretty close to 0. So when I add them all up, I don't get a lot. If the null hypothesis is not true, then some of these, I mean, the evidence for that is some of these are going to be quite a ways away from 0. They'll have a big z value, and because we square them, the positive ones are not going to cancel the negatives. They're all just going to pile up. And so the bigger this thing gets, let's call him X, our test statistic. The bigger he gets, the more evidence we have that the null hypothesis is wrong. We're getting more and more values further away from what should be our expected value, ni theta. So how far is too far? Like, where do we draw the line? Well, we use the chi-square distribution with k minus 1 degrees of freedom. So that's what we're going to do. We're going to take our sample data. We're going to calculate this x right here. Looks a little bit intimidating, but we'll find a slick and easy way to do that, hopefully. And then we'll just compare it to the appropriate chi-square random variable. Okay, to help us with this, there's a identity. So let me show you. So let's let Fij, actually Fi1 be the observed values. F stands for frequency. We're counting sample values, observed successes from population I. And we're going to let Fi2 be the observed failures. So this is going to be our xi value, and this is going to be ni minus xi from population I. And then we have our expected, if the null hypothesis is true. I1 is the expected EXP failure successes. So the sub 1s are successes in the second subscript. The sub 2s are failures. From population I. And similarly, EI2 is the expected failures from population I. Fi1 is xi, Fi2 is ni minus xi. EI1 is ni theta, the common theta value. I think as I call it theta I. Doesn't really matter. We're doing our calculations as if the null hypothesis is true. All thetas are the same. Let's just leave it as theta. And then this down here would be ni1 minus theta. Probability of a failure times the sample size. Okay, and you can see that those expressions are represented in our test statistic X. So here's the identity, which I'm going to state and not prove, and I'm going to ask you to prove it on the homework. Let's call this a theorem. I'm not sure if it's a theorem, a numbered theorem in the book. Let me check real quick. It's not. But we're going to call it a I don't know, 13.b bonus. As described, so in the context of section 6, I can calculate X, our test statistic, which we understand it, the distribution, I mean, with a little bit of fuzziness about the degrees of freedom, I equals 1 to k, xi minus ni theta hat squared over ni theta hat 1 minus theta hat. That is the same as the double sum, I equals 1 to k, j equals 1 to 2. And then we take Fij, the observed values, minus the expected, square those, and divide by the expected. Those are the same. And this guy is easier to calculate, as you'll see. Any questions? If so, send me an email. Or at 11 o'clock tomorrow, Friday, I will be on Zoom. And yesterday, no one showed up. That's okay with me. But between 11 and 11:50, I'll be on Zoom. So if you have any questions, Zoom in. I think the link, I posted it on Foxtel. I think it's in the top panel. I also sent the link out in an email yesterday morning, Wednesday morning. All right, so what I want to do is show you how to do that calculation. And I'm going to do this one, not that one. And I'm going to do this using problem number, just picked a problem out of the book. I picked an odd number one so I don't spoil the even ones for you. Let's see, number 53. On page 378. So let me read the problem to you, and then we'll do the calculations. I'm going to do them in Excel. You know, our value of k, it's never going to be super large, so you can do them by hand. I know Timmy likes to do them by hand. And what I mean by hand is the individual terms of the series. You use a calculator, and then you just kind of write them all out and add them up. I'm going to use Excel, and you do whatever seems comfortable for you. So, I said 53, I mean 73. So if 26 of 200 tires of brand A failed to last 30,000 miles, whereas the corresponding figures for 200 tires of brands B, C, and D were 23, 15, and 32, test the null hypothesis there is no difference in the durability of the four kinds of tires. They tell us to do it at the 5% level of significance. I'm going to do a p-value test. And then we'll compare our p-value to alpha equals 5%. We can do the test that way. Because I'm using Excel and, you know, chi-dist is just right there waiting for me to use it. So let me pull my computer down. And I should be able to share my desktop. Let me get it the way I want it. And then the Zoom, share screen. Okay, you should be looking at an Excel spreadsheet. I'm going to zero out all of these. There's the p-value, 0.068. So remember that. We'll make sure we get it right. This is just an Excel spreadsheet. So I read the numbers pretty fast. One thing nice about this problem is the sample sizes are all the same. You notice they have 4 populations. They call them A, B, C, and D, but clearly that's 4. And what we're interested in is the proportion of tires that fail within 30,000 miles. So these are real similar populations. We're 30,000 miles. We're looking at just 4 different brands of tires. So it's a perfectly good context to use this technique. Very similar populations. It's kind of weird in that we're calling a success the ones that failed. But, you know, we can do that, no problem. Kind of bugs me when these guys are sitting off to one side. So let me true them up. Oh, yeah, much better. All right, so I just punched the raw data in. And you probably didn't catch the numbers, but there were 26 from brand A, 23, 15, and 32. So you can see there's some differences there. Brand C was the best in our samples. Only 15 of the tires failed, whereas brand D was the worst. But is it statistically significant, or can we just explain that due to randomness? I mentioned before the sample sizes are the same, so I kind of cheated a little bit, and I just use a formula. You can see it 200 minus A6 and copied it down. You know, when the sample sizes are the same, some nice things happen. That's one of them. Another one is that the expected values are all the same. Under the null hypothesis, let's see, somewhere I calculated my theta hat. I summed all of these guys up. Should be able to see the formula here. There it is. And normally I would sum all the ends up, but I could do 200 times 4 in my head, and I got 800. So based on the raw data, under the null hypothesis, our theta hat, and let's push this guy over to the right, is 12%. Okay, and now we build in our data, and all we have to do is say equals, and then we're going to take in the numerator, we're going to take this number, observed minus expected, square the quantity, and divide by expected. So 26 is super close to 24. Like, that gives us no evidence whatsoever. And notice the chi-square, it's a tiny little number. That's good. Now let's copy that guy down. And you can see the most extreme case contributes the most to our chi-square, 3.375. I think I can copy this formula over, and it will change all the references. Yeah, it moved us over to column B. Perfect. And so I can just copy that thing down. And because, notice these values are a lot smaller, that's because we're expecting 176. And, you know, with that many, we would expect greater variability. I'm trying to think if that makes sense. So it takes a greater variability to really get the attention of the chi-square statistic. So again, tire C, that's the biggest one. That's the one that deviates the most. But the question is, is any of this significant? Well, let's sum them all up. So I'll just do a sum, all 8 values, and this will be my chi-square value, 7.1. Now, if this was a z-test, we would say, oh, reject it with authority, like impossible. But we're not so good with the chi-squared. We know the expected value is the degrees of freedom, which for us is 3. We have 4 populations, but we're replacing a parameter, theta 0, with an estimate, so it goes down by 1. So this is bigger than the mean, but is it significantly bigger? Well, we can look up a table in the back of the book, or we could just use Excel, chi-dist. So we want to know, like, for our value with 3 degrees of freedom, and there's that number, 0.068. So that is greater than alpha. Greater than alpha. So we fail to reject. You know, man, we should have just picked alpha to be 10%, and then we could reject it. But A better way to do it maybe is just to report the p-value and let the reader, the folks at Goodrich and Firestone, they can make up their own minds about what the truth is. All right, there you go. K equals 4. Not using theta 0, but using theta hat, replacing theta 0, theta hat. So I promised I would tell you the difference. If we have a specified value of theta 0, all of the populations have this value of theta, then we're going to use theta 0 in our test statistic. We're not going to use theta hat. We're going to use theta 0 there, there, and there. Oops. Let me stop sharing my screen, and you'll see where there is. So we'll use theta 0 here. We'll use it there and there. And now we're not using an estimate in place of a parameter. So our degrees of freedom would be the number of chi-squares we're adding up. So let me show you the formula. Everything is contained right here. If we have a theta 0, we're just going to use that pre-specified value, and we're going to compare it to chi-squared sub k. That's the only difference. All right, I'll assign you some homework before long. You can look forward to that. And again, I'll be in my office on Zoom at 11 o'clock Friday. So check in if you need to. Just check in and say hi. Let me know you're around. All right, talk to you later. Bye.